this tutorial, I'll show you different methods to rigidly align your dataset. We'll go from randomly aligned meshes to a well-aligned set of meshes, from where it's much simpler to establish point correspondence. Hi, and welcome to Coding with Dennis. My name is Dennis. This here is the second tutorial in the series on how to create statistical shape models. Aligning a dataset can be tedious, but the time spent here will be well worth it, as it'll make it much simpler to establish point correspondence and thereby creating great statistical shape models. In this tutorial, we'll go over 4 different methods for aligning a dataset. First off, center alignment. The first method simply aligns the mesh to the center of the scene. This might be enough if, for instance, the rotation of your meshes is already normalized. Second, principal component alignment. The second method calculates the principal direction in the data and aligns these to the global coordinate system. This method works great when a major axis can easily be determined from the data. Third off, landmark annotation. The third method requires manually placing landmarks on all the meshes that should be aligned. This here is obviously time consuming, but at the same time it's guaranteed to work every single time. Finally, we'll look at a fully automatic method that iteratively aligns 2 meshes. Also have a look at the official Scalismo documentation, which also has a guide on rigid alignment. But first, let's start with original alignment. Original alignment is a method that works well if the meshes are similar in orientation. Specify where the file is located, load in the mesh in Scalismo, calculate the center of the mesh, then convert the point into a translation and apply the inverse of the translation to the original mesh. If you have some metadata or some domain-specific knowledge that hints about the applied rotation, translation, or even scaling, you can also build up your own transformation by specifying each of the components. Classes also exist in Scalismo that then apply the different transformations one after another as hinted by the name. For instance, the class name translation after scaling after rotation 3D. The rotation will be applied first, then scaling, and then translation. If the meshes have a major directional axis, then the PCA alignment could be useful. Note, however, that the axis direction might be opposite. So you will need to manually go over and rotate the meshes by 180 degrees around some of the axes. For this example, I'll show you a few femur bones where there's a clear major axis direction. Initially, the femur bone is well aligned, so we'll first create a random translation and rotation and apply that to the mesh. Then we'll create a PCA alignment function, which will return a transformation which will eventually apply to the mesh. In the function, first we'll calculate the center of the mesh. Then we'll calculate the covariance matrix of all the mean free points of the mesh. And finally, we'll compute the rotation matrix using singular value decomposition. For the manual annotation, let's start an instance of Scalismo UI and load a mesh. Then we click the landmarking tool and start clicking landmarks. Either you can make use of the order the landmarks are defined, or as alternative, I like to give meaningful names to landmarks. If you have a large dataset, you can also code up a semi-automatic method to help automatically change the landmark names. After landmarks, I click for each and every mesh in the dataset. It is time to align our data using Scalismo. We first load in the reference landmark file, as these are the ones that we would like to align our data to. We then read in the target mesh and landmark files. We then calculate the transformation using the landmark transformation, apply the transformation to the mesh and the landmark, and save the mesh in a new aligned folder. Also, a good idea is to visualize the actual aligned mesh output to be sure that all your landmarks were correctly clicked. In the example, all the landmarks are paired based on the index in the landmark file. If we instead have the names of the individual landmarks, we can match the names in the 2 landmark files instead. And finally, let's perform the alignment using automatic ICP alignment. This implementation is also in one of the tutorials provided on the Scalismo website. Here we'll create a function called alignment rigid ICP, which takes in a reference. This is the mesh that we would like to be transformed. Then target, this is the ideal alignment that we would like our reference here to have. The number of points to estimate the transformation upon, and the number of iterations to take. And finally, this function will just return a triangle mesh, so the reference mesh that has been transformed. Inside here, we call a recursive function ICP rigid alignment, which takes in the moving mesh. This starts out with the initial point of the reference mesh, then the point IDs that we would like to estimate the transformation upon and the number of iterations. And then in the recursive function, we'll just decrease this iteration value in every single iteration. If the number of iterations is 0, then we'll simply just return the value that we have so far calculated in the value moving. Otherwise, first we'll calculate the corresponding values, the corresponding points in the target mesh based on where we are now with our reference, the moving mesh. And for that, we'll implement a new function, attribute correspondence. In here, we simply loop over all the point IDs in the moving mesh, find the point, and find the closest point on the target mesh. And then we return these 2 points. Now in our function, we calculate the transformation using landmark registration, just as we did in the landmark annotation example. Then we apply this transformation to the mesh and iterate the function again. This method will iteratively estimate the corresponding points between the 2 meshes, calculate the transformation between the meshes, and then apply the transformation to one of the meshes. This method works well if the orientation of the meshes has already been solved. Often I use this as an additional alignment step after aligning the meshes with a few landmarks. If one of the meshes is flipped around an axis, the method might end up in the wrong orientation. Just look at here in my small example of one of the femur bones being flipped around one of the axes. In reality, you might often end up using a mixture of the above mentioned methods. For the vertebra example, I have defined a few manually clicked landmarks as also available in the GitHub repository. Depending on the dataset you're working with, a different mixture might be useful. And that's basically all there is to rigidly aligning data. Of course, a lot of more advanced methods exist out there, but for building simple statistical shape models from a relative small set of data items, I'm confident that the provided methods will take you far. In the next tutorial, we'll look at different strategies for choosing a reference mesh for your statistical shape model. That was all for this video. Remember to give the video a like, comment below with your own shape model project, and of course subscribe to the channel for more content like this. See you in the next video.